In this learning module, you will learn the basics of hydraulic pumps. The following learning objectives are to be achieved in this module. You should be able to describe the basic functions and operating principles of hydraulic pumps. You should be able to state important distinguishing features of standard pumps and explain their importance. You should be able to list 6 types of standard pumps and their most important distinguishing features. As a typical representative of fixed pumps, you should be able to explain the layout, function, and features of external gear pumps. As a typical representative of variable pumps, you should be able to explain the layout, function, and features of bent axis and swash plate pumps. You should be able to calculate pump flow and hydraulic pump power. You should be able to define and differentiate between volumetric and mechanical efficiency, as well as total efficiency, and sketch their qualitative progressions as a function of load pressure. This learning module gives you several opportunities to check your progress. These quizzes are not saved or reviewed. You can repeat or skip the quizzes. At the end of the module, there is a final test which you have to pass in order to move on to the next learning module. In a hydraulic system, hydraulic pumps act as energy converters. They convert mechanical energy coming, for example, from a diesel engine into hydraulic energy. The mechanical energy is used to generate flow in the hydraulic circuit. Here you can see the principle using the example of a wheeled loader with hydrostatic travel drive. The drive energy is supplied by the vehicle motor and converted in the hydraulic pump into hydraulic energy. The energy stored in the hydraulic fluid is determined by pressure and flow. Hydraulic motors at the mechanical transmission then convert the hydraulic energy back into mechanical energy to drive the wheeled loader. In this example, the hydraulic pump draws hydraulic fluid from a tank under atmospheric pressure and feeds it into the hydraulic system. As long as there is no resistance to this flow, there is no pressure. The fluid is simply conveyed. Pressure builds up once the flow must overcome resistance. In our example, it is a force that is exerted on the piston of a hydraulic cylinder. The pressure builds until it is able to overcome the resistance. This means that, strictly speaking, notions such as pump pressure or generating pressure with the pump are incorrect. The pressure generated in a system is the product of load and various kinds of resistance working against the flow generated by the pump. This can be in the form of pipe resistance and resistance caused by flowing through components. The circuit symbol for a hydraulic pump is taken from its function. A circle for energy converter with a triangle pointing outward to indicate flow direction and the conveyed medium. A fluid in this case. The pump is driven by a shaft. A curved arrow indicates the direction of rotation of the shaft. Here, clockwise when looking at the end of the shaft. The direction of rotation is only indicated if it is necessary, for example, to properly connect a diesel engine. The pump requires working lines at the inlet and outlet. The ports are generally designated S for suction port and P for pressure port. If the flow is variable, it is indicated by a diagonal arrow. Another line returns the pump leakage to the hydraulic reservoir. The port for this line is designated by a T or L. As with all hydraulic circuit symbols, this one also only indicates the function and installation position of the component. The symbol does not indicate the type of pump, for example, a gear pump or an axial piston pump. Very good, that's right. The flow generated by a hydraulic pump depends primarily on its displacement volume. Displacement volume in a hydraulic pump is the volume of hydraulic fluid that the hydraulic pump displaces per rotation of its shaft. The unit for this displacement volume that is used in hydraulics is cubic centimeters per rotation. Hydraulic pumps are distinguished whether this displacement volume is fixed or variable while in operation. Hydraulic pumps with fixed displacement are called fixed pumps. Their flow generally can only be varied with the pump speed. Hydraulic pumps with variable displacement are called variable pumps. With variable pumps, flow can be adapted to the needs of the work elements. The pump only provides as much fluid as needed. The flow also depends here on the pump speed. As an example of a fixed pump, we are showing here a bent-axis axial piston unit type A17FO for open circuits. There are also axial piston pumps that work as variable pumps. Here you see a bent-axis variable pump type A4VG for closed circuits. Hydraulic pumps can be designed to rotate clockwise or counterclockwise or be reversible. This direction of rotation must be observed when running the pump. Running the pump in the wrong direction of rotation for extended periods can result in malfunction and even damage. The direction of rotation is indicated to the user by the circuit symbol for the pump. For consistency, the direction of rotation is always viewed from the drive end to the pump shaft. Clockwise rotation or counterclockwise rotation. In our example, you see two fixed displacement pumps with different direction of pump shaft rotation, but with the same flow direction.
Very good. All your responses are correct.
Pumps have numerous, sometimes completely different construction principles. Pumps with the following displacement elements are common in hydraulics: gears, vanes, pistons. As with all technology, there is no ideal solution for all applications. Since each principle has advantages and disadvantages, certain pump designs have become accepted for certain applications over time. The most important ones are shown in this overview. Some pump types can be designed in principle only as a fixed pump. These include external gear pumps. Axial piston pumps come in bent axis or swash plate design, and their displacement volume cannot be varied. These are primarily used for open circuits. Other bent axis and swash plate pump designs are variable pumps. This means their displacement volume is variable. They can be used for open or closed circuits depending on their design. A typical representative of fixed pumps is the external gear pump. It is very common primarily in the mobile hydraulics sector and in industrial hydraulics. Apart from special designs, external gear pumps meet the needs of normal hydraulics. A correspondingly large range of specifications is available. The most important parameters for the AZPF pump from the Rexroth range of products is shown here as an example. In circuit diagrams, it is given the circuit symbol for a fixed pump, and in certain circumstances, the direction of rotation is indicated. We will now explain the layout and function of external gear pumps, as well as the resulting advantages and disadvantages. The most important components of an external gear pump can be seen here in the sectional view. On the drive shaft 1 sits the driving gear 2. The driving gear in this example rotates clockwise, while the driven gear 3 rotates counterclockwise. Both have external gearing, which is why they are called external gear pumps. The drive shaft and the axles 4 of the driven gear are mounted in slide bearings 5 to absorb the radial shaft forces. 2 bearing blocks 6 hold the slide bearings and also set the distance between the two gears. The distance is such that the gears mesh with minimal axial clearance. The housing 7, which is often made of an extruded aluminum profile, houses the suction port S and the pressure port P. The housing is closed with cast iron covers 8 and sealed with housing seals 9 and a shaft seal ring 10. External gear pumps are displacement pumps. This means they generate flow by displacing hydraulic fluid. When the gears rotate, tooth gaps open on the suction side. When suctioning, the increasing space produces negative pressure and fluid enters the pump. The tooth gaps fill with fluid. The rotation carries the fluid to the pressure side. Here, the tooth gaps close again and fluid is displaced into the connected hydraulic system. Once the flow has to overcome resistance on the pressure side, such as to lift a load, pressure builds. The constant opening and closing of the tooth gaps results in a pulsating flow, causing pressure pulsations and noise. Their simple design, few parts, extruded profile housing. External gear pumps are inexpensive to manufacture. Their robust layout allows for high power density. That is, the overall installed size is relatively small compared to their hydraulic power. They can also be designed for harsh operating conditions. The pulsating flow, however, results in pressure pulsations and noise emissions. It is also not possible to avoid. Hydraulic fluid leaks from the pressure side to the suction side through gaps in the sides or the tooth crests of the gears. This impacts the efficiency of the pump. Limiting these losses requires greater engineering effort. However, the aluminum housing makes the pump sensitive to pressure peaks.
Very good. All your responses are correct.
Another variant is the axial tapered piston fixed pump in bent axis design. The example shows an A17FO Series 10. It is primarily used in mobile hydraulics in the area of commercial vehicles for truck superstructures and dump trucks in open circuit. The circuit symbol for this kind of pump is the symbol for a fixed pump with internal leak oil return and an air bleed port. In order to meet the demands of the commercial vehicle sector, the A17FO comes in 5 different sizes, from 23 to 107 cubic centimeters per revolution. Depending on size, the pump has a maximum speed range of 2,000 to 3,050 revolutions per minute at a nominal pressure of 350 bar, with temporary maximum pressure up to 400 bar. Higher speeds are possible by increasing inlet pressure at the suction port S. The bearing kit, which absorbs forces acting in the axial and radial direction, is assembled on the drive shaft 1. 2 shaft seal rings 2 are used to seal the pump from the outside and from the transmission. The one-piece tapered pistons 3 catch the cylinder without the need for a drive shaft. Due to the spherical surface of the control plate 5, torque-free support of the cylinder 4 is provided. Due to the bent axis design, torque is generated directly on the drive shaft. The radial loading of the pistons on the cylinder is very low, which reduces wear, increases efficiency, and improves starting torque. The port plate 6 contains the suction port S and the pressure nipple 7. The installation position of the pressure nipple indicates the direction of drive rotation. This can easily be modified by changing the position of the pressure nipple. The drive shaft is driven by the torque and speed of a drive motor. The drive shaft causes the pistons to catch the cylinder and rotate it. The cylinder slides on the control plate. With each revolution, the pistons extend into the cylinder bores. During one revolution, each piston returns to its initial position through the top and bottom dead centers. This causes the hydraulic fluid corresponding to the displacement to flow through the 2 discharge ports in the control plate. Hydraulic fluid enters the increasing piston chamber on the suction side. At the same time, hydraulic fluid is pumped out of the cylinder chamber and into the hydraulic system on the high-pressure side. The hydraulic pump works in an open circuit, taking hydraulic fluid from the reservoir and feeding it through a directional valve to the consumer, such as a cylinder or hydraulic motor. The hydraulic fluid returns to the reservoir from the consumer through the directional valve. The A17FO fixed pump is specially designed for use in commercial vehicles. The compact, lightweight aluminum housing allows the pump to be installed easily in tight spaces, which is often the case with commercial vehicles. This gives this large-angle machine with a 40-degree swivel angle a high power density, small dimensions, and optimal efficiency. The sealing rings on the tapered pistons provide excellent self-priming performance. An internal leakage return line through the port plate and control plate makes an external drain line unnecessary. Due to the noise grooves and corresponding rotation of the control plate, the pump can easily be adapted to the different directions of rotation and is also still noise optimized. Another variant is the axial piston fixed pump in swash plate design. This example shows an A4FO Series 30 and 32. It is primarily used in mobile hydraulics in road rollers and concrete pumps, in the industrial sector in hydraulic presses, and in steel mills in open hydraulic circuits. The circuit symbol for this kind of pump is the symbol for a fixed pump with internal leakage return line and a measuring port X3. Ports T1 and T2 are used to bleed the axial piston pump. The A4FO comes in 8 different sizes, from 16 to 500 cubic centimeters per revolution. Whereas the smaller sizes, 16 to 40, are also used primarily in mobile hydraulics, the other sizes, 71 to 500, are used in industrial hydraulics. Depending on the size, the pump has a maximum speed range of 1,320 to 4,000 revolutions per minute at a nominal pressure of 400 bar, with temporary maximum pressure up to 450 bar. Higher speeds are possible by increasing inlet pressure at the suction port S. The rotating shaft 1 catches the cylinder on the splines. The shaft seal ring 2 is pressed into a clamp collar to seal the pump. The cylinder 3 rotates with the drive shaft, catching the 9 pistons with slipper pads. 4. The slipper pads 5 support the pistons on the sliding disc 6. The slipper pads are hydrostatically mounted, slide-bearing, to the sliding disc by the retainer plate 7 and retainer ball 8. The housing 9 is designed to allow the sliding disc to tilt, which allows the piston slipper pads to extend and retract. The forces at work in the hydraulic section of the rotary group, that is, the cylinder with pistons and control plate 10, are in equilibrium. The principle of the spherical control surface, its lubrication, the pre-charge pressure of the cylinder with springs, etc., is comparable to the function of the bent axis rotary group. The port plate 11 contains the suction 12 and pressure ports 13. The drive shaft is driven by the torque and speed of a drive motor. The drive shaft catches the cylinder using the spline and rotates it. With each revolution, the pistons extend into the cylinder bores. The slipper pads are held on the sliding surface of the swash plate and guided by the retainer plate. By the inclination of the swash plate, each piston moves during one revolution on the top and bottom dead center back to its initial position. This causes the hydraulic fluid corresponding to the displacement to flow through the 2 discharge ports in the control plate. Hydraulic fluid enters the increasing piston chamber on the suction side. At the same time, hydraulic fluid is pumped out of the cylinder chamber by the pistons and into the hydraulic system on the high-pressure side. The fixed pump A4FO in swash plate design is specially designed for hydrostatic drives in open circuit. The fixed swivel angle makes the flow proportional to the drive speed and the displacement volume. The displacement volume can only be increased by increasing the drive speed. The large cross-section of the suction port ensures good suction performance with low noise. The hydrostatically mounted slipper pads also extend expected service life. A special range with through drives on the port plate makes various pump combinations possible. Variable pumps also come in bent axis and swash plate design. This example uses an A7VO Series 63. a bent-axis variable pump with an axial tapered piston rotary group for hydrostatic drives in open circuit. It is primarily used in industrial applications as well as mobile hydraulics in equipment such as excavators, cranes, and concrete pumps. The circuit symbol for this kind of pump is the symbol for a variable pump with internal leakage return line and a flushing port U. The housing area is connected to the suction chamber, so a drain line is not required. The A7VO comes in 5 sizes, from 28 to 160 cubic centimeters per revolution, and with a broad selection of controllers for all open circuit applications. These include power control, hyperbolic, pressure control, hydraulic control, positive control, and electro-proportional control. The bearing kit that absorbs axial and radial forces sits on the drive shaft 1. A shaft seal ring 2, a snap ring, and a supporting disc installed in the one-piece housing are used to seal the pump. The one-piece tapered pistons 3 catch the cylinder without the need for a drive shaft. The spherical surface of the lens plate 4 provides torque-free support for the cylinder 5. Due to the bent-axis design, torque is generated directly on the drive shaft. The radial loading of the pistons on the cylinder is very low, which reduces wear, increases efficiency, and improves starting torque. The port plate 6, or pump controller, houses the suction port S and the pressure port, as well as all regulating parts. The direction of rotation of the variable pump is fixed and can only be changed with extensive rebuilding. The drive shaft is driven by the torque and speed of a drive motor. The drive shaft and pistons catch the cylinder and rotate it. The cylinder slides on the lens plate, which contains 2 control slots. With each revolution, the pistons extend into the cylinder bores, the size of which depends on the swivel angle of the bent axis return group. During one revolution, each piston returns to its initial position through the top and bottom dead centers. This causes the hydraulic fluid corresponding to the displacement to flow through the 2 control slots in the lens plate. Hydraulic fluid enters the increasing piston chamber on the suction side, where the control slot is large. At the same time, hydraulic fluid is pumped out of the cylinder chamber into the hydraulic system on the high-pressure side, which has the 2-part control slot. The swivel angle of the bent axis rotary group is infinitely variable. Changing the swivel angle alters the piston stroke, altering the displacement. The swivel angle is changed hydraulically by the stroking piston. This causes the cylinder, including pistons and lens plate, to swivel. The lens plate is loosely mounted in a slipway. Increasing the swivel angle increases displacement, while decreasing the swivel angle decreases displacement accordingly. The bearing should be flushed when operating at 0 stroke for long periods, more than 1 minute. When unpressurized, a return spring swivels the pump back to its initial position of VG max. The A7VO variable pump is specially designed for use in open-circuit, mobile, and stationary applications. The maximum swivel angle of 25 degrees gives the bent axis rotary group high power density, small size, and optimal efficiency. This robust compact pump is also resistant to microcontamination, as evidenced by its long service life. A broad range of control devices are available for all mobile and stationary applications. The hyperbolic power control option is externally adjustable even when the pump is running. The A4VG is an axial piston variable pump in swash plate design for hydrostatic drives in closed circuit, primarily for all kinds of travel drives. A hydraulic system is closed when the hydraulic fluid returning from the consumer is fed directly back into the pump. There is a high pressure and a low pressure side depending on the direction of loading or discharge torque on the consumer. While the A4VG pump is used for various applications in mobile hydraulics, it is primarily found in speed-regulated hydrostatic travel drives, as used in wheeled loaders, telehandlers, forklifts, airport ground support vehicles, and commercial vehicles. It is also used in hydrostatic drives with fixed drive speed, such as those used in road construction machines, bulldozers, excavators, concrete machinery, cranes, agricultural and forestry machinery, and heavy-duty transporters. The A4VG comes in 8 different sizes, from 28 to 250 cubic centimeters per revolution. Depending on size, the pump has a maximum speed range of 2,400 to 4,250 revolutions per minute at a nominal pressure of 400 bar, with temporary maximum pressure up to 450 bar. Since there are now applications in mobile hydraulics that require higher pressure levels, the latest version of the A4VG, the Series 40, is designed to have a nominal pressure of 450 bar and a maximum pressure of 500 bar. The circuit symbol for the A4VG is the symbol for a closed-circuit variable pump 1 that swivels on both sides. Infinitely variable swivel angle from neutral position. Reversible direction of drive rotation, shown here as clockwise. In addition to the air bleed port, R, the pump has 2 external drain ports, T1, T2, that have to be connected depending on the installation position. It is possible to add other units on the through drive for a tandem version. Every component required for safe closed-circuit operation is integrated into the pump. The internal gear pump 2, which works in an open circuit, the boost pressure relief valve 3, both high-pressure relief valves 4, with feed function pressure cutoff 5, the hydraulic control 6, and the control module 7 that changes the swivel angle of the pump. In axial piston units in swash plate design, the pistons are arranged parallel to the drive shaft 1. They are guided in the rotating cylinder 3 and mate with a stationary cradle using slipper pads 4. The drive shaft and the cylinder are connected by a spline. The shaft seal 2 is pressed into the one-piece housing and secured by a special snap ring to seal the pump. The port plate 5 houses all of the assembly groups needed for operation and to safeguard a closed-circuit system. These assemblies are the boost pressure relief valve 6, pressure cutoff 7, and the high pressure relief valve 8 with feed function. The internal gear pump 9 supplies the system with sufficient hydraulic fluid at all times and maintains the hydrostatic bearing between the piston slipper pad and the cradle. The hydraulic control 10 uses the cradle to keep the rotary group in the neutral position when in standby mode. When a stroking chamber is pressurized with hydraulic fluid by the control module 11, the swivel angle and piston stroke change, varying the displacement. The drive shaft is engaged by a drive motor, generating torque and speed. The cylinder rotates with the drive shaft, catching the pistons. In the neutral position of the cradle, the pistons have no movement, so no hydraulic fluid is delivered here. The pressure on each side of the rotary group is equal. This is the boost pressure that the internal gear pump uses to supply the rotary group with hydraulic fluid while building the hydrostatic bearing between slipper pad and cradle. The swivel angle of the cradle is infinitely variable. Changing the swivel angle alters the piston stroke and, with it, the displacement. Increasing the swivel angle increases displacement, while reducing the swivel angle decreases displacement accordingly. Depending on the direction of the swivel angle, the top or bottom of the rotary group is charged with high pressure. The smooth change of the flow direction by moving the swash plate through the zero position causes at the hydraulic motor a smooth changing direction of rotation. That is, the vehicle can thus go continuously forward or backward. The A4VG variable pump in axial piston swash plate design is specially designed for hydrostatic drives in closed circuit, including travel drives with fixed and variable drive speed. Flow is proportional to drive speed and displacement. Flow direction changes smoothly as the swash plate is moved across the neutral position. A wide range of adaptable control modules with different control and regulating functions is the perfect solution for all important applications. Two pressure relief valves on the high-pressure sides protect the hydrostatic transmission, pump and motor from overloading. The A10VO is an axial piston variable pump in swashplate design for hydrostatic drives in open circuits. This pump is mainly used in the medium pressure range for supplying the working hydraulic in different applications. In an open circuit system, the hydraulic fluid flows from the tank to the hydraulic pump and from there via the control block to the consumer, such as hydraulic cylinder or hydraulic motor. From the consumer, the pressure fluid flows back to the tank. The A10VO of the Series 52 and 53 are available in 8 different nominal sizes, from 10 to 100 cubic centimeters per revolution, and an extensive range of control modules. These are the hydraulic pressure and flow control, the electro-hydraulic pressure control, power control, and the electro-proportional swivel angle control. The pump works according to the nominal size in a maximum speed range from 2,300 until 3,600 revolutions per minute at a nominal pressure of 250 bar, or in a short period with high pressure of 315 bar. The circuit symbol for the A10VO is the symbol for an open circuit variable pump that swivels on one side. The swivel angle is infinitely variable. A compression spring keeps the rotary group at the maximum swivel angle when the pump is in standby mode. Drive rotation is only possible in one direction. There are pumps with clockwise and counterclockwise rotating drive speed. The pump has 2 drain ports, L1, that must be connected depending on the installation position. In axial piston units in swashplate design, the pistons 4 are arranged parallel to the drive shaft 1. They are guided in the rotating cylinder 3 and mate with the stationary cradle 7 using slipper pads 5. The drive shaft 1 and the cylinder 2 are connected by a spline. The shaft seal ring 2 is pressed into the one-piece housing and secured by a snap ring to seal the pump. The slipper pads 5 are mated with the sliding surface of the cradle by a retainer plate 6. The discharge ports in the distributor plate 8 suction as well as pump the fluid according to the swivel angle. The spring 9 holds the cradle at the maximum swivel angle when the pump is in standby mode. Due to the corresponding control valves 12 and stroking piston 10, the pump can be adapted to the appropriate displacement automatically. The drive shaft is driven by the torque and speed of a drive motor. The drive shaft catches the cylinder using the spline and rotates it. With each rotation, the pistons and slipper pads extend into the cylinder bores, the volume of which depends on the angle of the cradle. The slipper pads are held on the sliding surface of the cradle and guided by the retainer plate. The pitch of the cradle during a revolution causes each piston to move over the bottom and top dead centers and back to its initial position. Hydraulic fluid is fed into and out through 2 control slots in the control plate according to displacement. Hydraulic fluid enters the increasing piston chamber on the suction side. At the same time, hydraulic fluid is pumped out of the cylinder chamber by the pistons and into the hydraulic system on the high-pressure side. The A10VO variable pump is specially designed for medium-pressure, open-circuit mobile applications. Stable bearings ensure long service life. An excellent power-to-weight ratio and small dimensions allow for high drive speeds. Short regulating times and good suctioning performance reduce noise when running. Various control devices are available depending on requirements. The function of a hydraulic pump is to generate flow. You already know how to calculate flow from the learning module Physical Principles. Flow, QV, equals volume V divided by time T. For pump flow, we use displacement instead of volume. This gives us the following relationship. pump flow QV equals displacement Vg divided by time T. Displacement is the volume of hydraulic fluid displaced by the hydraulic pump per revolution of its shaft. If we multiply this volume by the number of shaft revolutions per unit of time, we get the displaced volume per unit of time. The number of revolutions per unit of time is nothing more than the speed. This means we can also calculate pump flow using pump speed. Pump flow QV equals displacement Vg times speed N. The unit used for displacement in hydraulics is cubic centimeter per revolution. Pump and drive motor speed is indicated in revolutions per minute. Pump flow is indicated in liters per minute. Adding a conversion factor to the formula avoids having to convert the units. The numerical equation for pump flow is thus: pump flow QP equals displacement Vg times speed N over 1000. Here is an example of a simple calculation. An external gear pump from the Rexroth range is operated at 1,450 revolutions per minute. The displacement per revolution is 20 cubic centimeters. We want to find the pump flow in liters per minute. For simplicity, we use the numerical equation for the solution. The result is 29 liters per minute. We need the pump flow to calculate another parameter of hydraulic pumps, the hydraulic power. The hydraulic pump power is greater the greater the pump flow is. Pump power also depends on the pressure difference between the suction port and the pressure port. The greater the pressure difference, the greater the pump power. These two relationships give us the formula: hydraulic pump power P equals pressure difference delta P times pump flow QV. The common unit for pump power is kilowatts. Pressure and pressure difference are indicated in bar. 1 bar equals 1000 PA. If we also want to use pump flow in liters per minute, we again need a conversion factor. The numerical equation for hydraulic pump power is therefore: hydraulic pump power P is the pressure difference delta P multiplied by pump flow QV divided by 600. We continue with the sample calculation for pump flow. According to the pump's datasheet, the maximum continuous pressure is around 230 bar. We have calculated the pump flow to be 29 liters per minute. We want to find the hydraulic pump power in kilowatts. We use the numerical equation for the solution. The result is approximately 4.83 kilowatts.
Very good. All your responses are correct.
So far, we have not considered efficiency in our calculations of pump flow and pump power. As you already know, every technical process includes losses. In a hydraulic pump, both volumetric and mechanical losses occur. This means there exists volumetric and mechanical efficiency. Volumetric efficiency is based on losses of usable hydraulic fluid. A part of the flow suctioned by the hydraulic pump is lost inside the pump, for example, due to leakage. In a gear pump, for example, hydraulic fluid can leak through gaps between the gears and the bearing blocks. These volumetric losses reduce pump flow and, with it, pump power. Volumetric efficiency is the ratio of effective flow QVF pumped into the hydraulic system to the theoretically possible flow QVTH. We return to our sample calculation of pump flow. An external gear pump with a displacement of 20 cubic centimeters per revolution is operated at 1,450 revolutions per minute. The volumetric efficiency of the pump is 85%. we want to find the effective pump flow in liters per minute. For the solution, we first convert the efficiency formula to the unknown variable QVF. Then we can use the numerical equation for QVTH to calculate the actual effective flow. The result is 24.65 liters per minute. Mechanical hydraulic efficiency refers to losses due to friction. Friction generally occurs whenever moving objects come into contact, for example, in bearings, but also between the hydraulic fluid and the displacement chambers. These losses mean a higher drive torque is required for the operation of the pump than theoretically calculated. Mechanical hydraulic efficiency is therefore the ratio of theoretical drive torque, MTH, to actual effective drive torque, MF. The same ratio applies to drive power. We continue with our sample calculation. In the previous chapter, we calculated a hydraulic pump power of 4.83 kilowatts, 6.57 horsepower, for our external gear pump. This is the theoretical power that would be required to drive the pump if there were no mechanical hydraulic losses. The mechanical hydraulic efficiency of the pump is 95%. We want to find the effective power required to drive the pump. For the solution, we convert the efficiency formula for the unknown variable PF and calculate the effective drive power. We get a result of approximately 5.1 kilowatts, 6.9 horsepower. The effective drive power is higher than the theoretical value because we need more power due to friction losses to drive the pump than the pump outputs to the hydraulic system as hydraulic power. Total efficiency reflects all losses, volumetric and mechanical hydraulic. Total efficiency should therefore be less than either of the sub-efficiencies. As you already know from the learning module, Layout of a Hydraulic System, total efficiency is the product of sub-efficiencies. The total efficiency of a hydraulic pump is therefore the product of volumetric and mechanical hydraulic efficiency. Please note that efficiency is not a constant value. This means the efficiency of a hydraulic pump depends on the pressure difference. Typical characteristic curves for the three efficiencies can be seen in this diagram. Volumetric efficiency is relatively high. As the pressure difference increases, however, the volumetric losses begin to rise and efficiency is reduced slightly. Mechanical hydraulic efficiency is very low at low pressure differences. This means losses due to friction are very high compared to power output. As pressure difference increases, friction remains nearly the same at first, but the effective power increases strongly so that the efficiency increases quickly. Depending on the design of the pump, the efficiency curve can remain relatively constant over a wide range, or efficiency begins to drop after reaching the maximum value as shown in our example. The characteristic curve for total efficiency is then the product of the two sub-efficiencies for each pressure difference.